Hello. Today we cover 4 important extensions of linear programming. This video, along with the R code, is going to be up on my courses, so you can follow along and download the R files to correspond with the code. In addition, any reference made to the handout refers to the handout that we used in class and that which I uploaded previously onto my courses. So let's just briefly cover at a high level what we're going to focus on today. So we're going to do some very important extensions of linear programming, as we saw. So we're going to recap and look at one example of transshipment. Now, if you remember, transshipment is the situation where we have some number of nodes here, and it's going to an intermediary spot. It could be a break bulk warehouse. It could be a repack warehouse, whatever the case is, before it goes along to its final, however many, destination. Okay, so that type of network structure typically has outbound flows from a supply point. There's a receipt here, which has to balance out, and then they go outward. The next example that we're going to focus on today is something called maximum flow. Maximum flow is basically if I have a network with multiple nodes and connections, outbound here, there, and I have an origin, and then I have a destination. The goal would be to push things throughout the network in this direction and have them follow along whichever path and to maximize that flow. Often you'll see this type of scenario occur with a broadband network, with an electrical network. Anytime you need to maximize the flow, that's when you're going to see a situation like that. The third scenario that we're going to focus on is something called integer programming. Integer programming, as the name suggests, implies that the decision variables are all integers. So if I have a situation, for example, where I need to have my xij be in the interval 0 or 1, or rather, excuse me, a better way to frame that would be xij is equal to 1 or 0 under some conditions. Okay, that's what's called a binary. Okay, this would be a binary integer program. Okay, in other cases, though, we would have our xij, or really just our xi. If there's no flow, wouldn't have a j. If it's our xi, we just want these to be integers. So, for example, if I'm sending product quantities, having a continuous number seems kind of strange, right? Having 2.5 refrigerators doesn't make much sense. Okay, so what we do, we're going to cover a little bit about that. It's essentially a constraint that gets placed on the decision variables that they have to be integers. So it slightly reduces the optimality of the solution, but it brings it back to a practical scenario where you can't have intervals of things. You have to have complete products, is often the example that we use. And then the final example is we'll look at an integer program for a facility location. So I'm going to pivot over to R for 1 second here, and we're going to focus on the first problem. Share screen. Actually, I'm going to share my entire screen rather than just one window. Okay, so for the first problem, as I mentioned, we're going to be focusing on another example of a transshipment problem. And this is going to be the same scenario that we covered in the previous class. 16 of the handout. So here you're looking at a scenario where you've got 3 supply points, 2 inbound points or transshipment points, and 4 outbound points. And then you've got flows going like this in all directions here. Okay, so you've got 6 routes to the supply points. And then the kink here is that you've got kind of this back and forth flow at the supply points. And then ultimately each, or rather intermediary points, and then each intermediary point supplies the outbound point. Okay, so essentially are 17 decision variables. Okay, and these are our Xij. And so we have first for X1, we have X1, 4, X1, 5. Then we have X2. We have X2, 4, X2, 5. X3, these are our supply points. X3, 4, X3, 5. Then we have our supply points themselves. We have X4. So here we have the first route is going from X4 to X4 down to X5, and then we've got X5 coming back, right? So there's this 4, 5, and then you've got 4, 6, 4, 7, 4, 8, and 4, 9. You've got X4, 5, X4, 6. I'm just gonna save some time and write X9. Well, you know what? Let's be explicit. 4, 7, X4, 8, X4, 9. Okay. Then I have the same thing for my X5. Same insofar as it goes back and forth between 4. So if I start looking at X5, I have X5, 4, because there's that flow backwards. Then I have X5, 6, X5, 7, X5, 8, and X5, 9. Okay. So now when I look at the coefficients for each of these, for X1, the flows, I have 4 and I have 7. For X2, I have 8 and I have 5. For X3, I have 5 and 6. For X4, the cost is 2, down into 5. And then I have 6, 4, 8, and 4. I have 6, 4, 8, 4. From X5, it's 2 going back to 4. And then I have 3, 6, 7, 7. And there actually is an added complexity that I forgot about here, which is X3 also goes to 9 directly. So here we have X3 to 9. And on that cost, you have 7. Okay. So my objective function, as you can see, is to minimize Cij, Xij, where these, of course, are my costs. These are my flows. Right? So if I'm looking at this, my constraints then are relatively straightforward. They're the same we have, and I'm not going to explicitly write them out. I would suggest you follow along on the handout. But here then I have my supply, which I have my X1 has a max supply of 450, and X2 has a max of 600. The demand so you've got each node, of course, receiving the demand 6 through 9, 6 through 9, you've got a demand of 300 to 400. And of course, each of these is satisfied by a number of different variables coming into play. So each of them, for example, if we look at just 9, demand point 9, what we've got there inbound is we've got X4, 9. 4 goes directly into 9. We've got X5, 9. And we've got X3, 9. Together, taking the summation of all of these go into X9, and therefore that total sum has to be greater than or equal to 400, right? So if you take a look, basically my demand here, the constraints are identical to what we've seen previously, except for the fact that you've got 3 nodes going into 9. And then of course I have my flow, which is saying that no inventory at X4 or X5, location 4 and location 5. So when we take a look at what that looks like in R, okay, I have 17 decision variables, so I'm making my linear programming model, and you can call it whatever you want, but I'm just calling it, following along with the convention. 17 decision variables, okay? I set up my constraints in terms of supply. You'll take a look here. The indices, if we hadn't mentioned it previously, the indices correspond to the number of the decision variable. So this is saying the first decision variable, this is saying the second decision variable, saying the third decision variable, the fourth decision variable, so on and so forth. So here, my supply constraints are bound by that which I have at each of the locations. The intermediate nodes are my balance constraints, saying that what goes in must come out, corresponding to their index out to in. Similarly, my demand is, as we said previously, in this case, of course, I want to minimize my cost. So if I take a look at set dot objective function, you can see right there that that's a vector of all my costs on the outbound routes. This could be in thousands, millions, hundreds of thousands, etc. And when I run that model, what I end up getting is the solution, the optimal solution, assuming that these costs don't change. I can take a look here and you can see this is the flow that's being sent out of each of those nodes, okay? And you can dig into the model a little bit, but the model is solved successfully by doing this. The answers that correspond to each one. So we move on here. The next example we're going to look at is something called a maximum flow. So that was just to recap previously what we've done. Now we're going to look at a new example of something called maximum flow. The maximum flow in the context of a network, as I mentioned previously, the goal is to throughput as much as possible throughout the network. And so in this scenario, let's assume the following network. This isn't from the handout. We're going to make this up as we go along. Let's assume you've got a relatively basic network with 4 nodes. Node 1, node 2, node 3, and node 4. And let's say it's a directed network, so you've got a flow like this, and you've got a flow like this. You've got one from there to there, one from there to there, one from there to there. And let's say rather than costs, here what we have are the capacities along these routes. So this could be a basic logistics network, one. This could be a transmission network. This could be any network, okay? So what I'm saying is if I have this network and I want to maximize flow, here I have my matrix where I have one, 2, 3, and 4. 1, 2, 3, 4. And typically the convention is it's a from to. So we look from here to here. So here I just put whatever the costs are. And as you can see, there's nothing from 1 to 1. That wouldn't make too much sense. Sometimes you have a circular loop, but in this context, it doesn't make sense. In this case, do I have something from 1 to 2? Yes, and my capacity is 3. Do I have something from 1 to 3? Yes, and it's 2. Do I have something from 1 to 4? No. We're just going to put nothing there. In a matrix format, it would be represented as a 0. What do I have for 2? So node 2, I have 2 to 1. Nope, I have nothing there. I have 2 to 2. Nope, nothing there. I do have a 2 to 3, which would be 1 at my capacity. And I do have a 2 to 4, which would also be 1 in this capacity. What do I have for 3? 3, I just have it going into 4. So I'm going to put nothing, 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 and then my capacity of 3. And then 4 is the terminus, so there isn't anything there. We just leave it. So what does this problem look like from a linear programming standpoint? Well, what I want to do is I want to maximize Z, which in this case is equal to outbound flow. What's the outbound flow? It's x1 to 2 plus x2, excuse me, x1 to 2, x1 to 3, right? That's the goal. I'm trying to maximize the outbound quantity. That's my decision variable. And we don't have necessarily costs, we have capacities that are going on. So we're going to model those in a moment. So you'll see that. Now my constraints in the scenario, so I'm subject to the following. I'm subject to my capacity. So for the route x1, 2, that has to be less than or equal to what? 3. Can't put more than 3. For x1, 3, that has to be less than or equal to 2. What else do I have? What's the next flow? Next flow I have from 2 to 3. So for x2 to 3, that has to be less than or equal to 1. What's the next flow that I have? x2 goes into 4. So I have x2, 4, and that route has to be less than or equal to 1. What's the next route that I have? I have x3 to 4, right? So that route, x, not lambda, x3, 4, less than or equal to 3. And you'll notice each of the constraints corresponds to an element in the matrix, right? So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Each element in the matrix, therefore, corresponds to a flow. So similarly, if we had a circuitous route and we had something from 3 back to 1, for example, we could model that very simply. We might create a goofy looking graph, but it could happen. So those are my outbound constraints. Then I have my balance constraints because I'm not letting anything stay at 2 or 3. So ultimately, this is the same as the transshipment problem, where what I have is I have x 1, 2 minus x2, 3 should be, and excuse me, and I'm also taking away x2, 4 because I can't leave anything there. So I have in and then out, out, right? So I have the 1 flow into 2 and the 2 outflows. So minus x2, 4, that should equal 0. We should net nothing. The next one I have, what else is inbound? I have 3. So 3 has an occurrence that's coming in from 2, and it has an occurrence coming in from 1. So in that scenario, I should have x1, 3 in minus x2, 3 in minus x3, 4 is equal to 0. That should net me nothing at either of those locations, right? So if that's the case, then we put that into R as a graph, very simply using the same methodology that we've been using previously. Now here, I'm calling this a network model. I have 5 decision variables. My objective function, as indicated here, as you can see, is just one coefficient of 1 across each of the first 2. I have my outflow on the nodes. I'm corresponding my indices to the capacities, okay? I had my balance constraint right there. And actually I made a typo over here. This should be a plus because it's inbound. That which comes in must go out. There's only one outflow from 3, but there's 2 inbound sources of supply, which is why this right here is added up. So I put that into my model very simply, and you can see the coefficients will correspond to that as well. When I look at this model here, I'm sending 2 and 2, so you can follow along. So 2 goes out from 1 to 2, 2 goes out from 1 to 3. From 2 to 3, I'm sending the 2 that went in. From the next one, I'm sending 1, and so on and so forth. So I'm sending the max capacity. So here, I'm sending basically the max capacity on the route from 1 to 3, but I'm not setting the max capacity from 1 to 2 because I'm compensating elsewhere. But my objective, the max capacity that I can send in is 4. And if you take a look, that's all that 4 can receive, because the inbound routes from 3 to 4, the max is 3, and the inbound routes from 2 to 4, it's 1. So it should be 1 anyway, and the model holds. An example of maximum. Yeah. The next example we're going to follow along to page 20 of the handout. And here we're looking at integer programming. So this one we're going to go through rather briefly. You can take a look at it on page 20 of the handout. Here, the situation that we have, more of a, you can see the feasibility or the expansiveness of integer programming. And essentially what we've got is multiple projects that we're looking at. Each of them have present values and future cash flows. Ultimately, what we're trying to do is determine whether or not which project makes sense. So we can't invest in everything. We have a fixed capacity as it relates to our finances, of course. There's different cash flows in different years, and ultimately different viabilities, really. And so what we have to do is make a decision which project we invest in. Okay, so when we take a look at it, the project or the objective function is we're trying to maximize. I'll just write it shorthand here. 90 project P, which is the plan expansion, plus 40, and I'm writing this in thousands, 40 W plus 100 M plus 37 R. And these are new machinery or new product research. Each of these is going to be a binary variable, which means that it will be either 0 or 1. 0 or 1 indicating yes, we're going to do this, or no, we are not going to do this. So that's the objective function. The constraints correspond to each of the capital that's available per year. So if you look at year 1, you've got 15 P plus 10 W plus 10 W, 10 N or M, whatever the letter is, machinery, plus 15 R, less than or equal to 40. So what I'm saying is, whichever of these is 1, the summation, the combination of all of them has to be less than my upper bound in 40,000. Okay, what's the next year? Then I have 20P plus 15W. I have 0 on the next one for M, because there isn't any cash flow that's required or incoming, plus 10 on the R, that has to be less than or equal to 50. And you do this for each of the years. And then ultimately, what how do we maximize the future cash flows, or present value rather, in the case of each of these? So I set up the model. And the only difference here is that you'll notice in the set type component occurs in R, you'll see it right there. I'm saying variables 1 through 4 should be binary in nature. That's telling R that the solution cannot be either an integer, unbound integer, nor a continuous variable. They must be or one. So here I set my objective function with each of my coefficients to present value. I set each of my constraints upper bound. You'll notice the cases are zero cash flows in those years. You have a zero. Those have to be no more than an aggregate from what we have. I keep on be a maximum model. I want to maximize profit. So when I solve it and I get the variables in the objective function, what we can see, I'm pursuing the following. I'm pursuing the plant expansion because it's the one. I'm pursuing the warehouse expansion, and I'm pursuing the new machinery. I'm not investing in any project. By so doing, going to generate 90,000, 10,000, total of 140,000. I maximize my speed. The reason why, very likely, the machinery look at it that in year 2 and 3, machinery requires zero outlay of cash. Okay, so in this case, we've chosen optimally the following projects, and this is a binary program. Okay, the final problem that we're going to look at is an example of a facility location problem. So in essence, what you have, and now we're on page 22, in essence, what you have is each of these locations generates some type of monthly revenue. So you've got stores 1 through 10, and each of them correspond to, let me pull this up. Each of them correspond to a different revenue generated monthly. Okay, so store 1 is 127, store 2 is 83, and so on and so forth. Well, in this case, what I'm saying is I want to make a model, and what I want to do with that model is make a choice. And I want to maximize, so if I look at my objective function, I want to maximize my monthly revenue. In this case, my constraints are rather practical. So we take a look here. It does not want any stores closer than 2 miles to each other. And what I'm saying is, okay, so the circled stores are those which are 2 miles of one another. So the combination of those two can exist together is essentially the constraint. So 3 and 2 are not 2 miles from one another, but 3 and 1 are. So if I take a look here, well, each of these constraints is essentially saying either one or the other. Because all of the variables are binary, and I want to maximize my revenue, I need to make sure that indices 1 and 3, which correspond to stores 1 and 3, one or the other, because those two, as you can see, are circled, but 3 and 2 aren't. So what's the next one? 1, 2, and 4. 1, 2, and 4 all exist within the same circle. So together, the sum of all those variables has to equal 1, meaning it's one or the other. It can't be all of them. I do this for 4, 5, and 6. I do this for 6, 7, and 8. I do it for 8 and 10. I do it for 9 and 10. I do it for 9 and 6. And I have right there my constraints. So what I do when I solve this, and you can follow along what's happening to the left, so here, what I'm saying, apologies for that error. I'm not quite sure what popped up there. But here, what it's saying is we're going to locate in stores 2, 3, 5, 8, and 9. So we're going to choose a facility to be located along that line. Okay. And what that does essentially is maximize our revenue. So if you add up the monthly revenues, it could be in thousands, millions, hundreds, whatever. If you add up that revenue, it will collectively accumulate to 618. So when we locate in stores, I'll just type it, I'll see it. The interpretation, open stores 2, 3, 5, 8, and 9. So similarly, do not open stores 1, 4, 6, 7, or 10. Okay. So one more example. Now, this I just wanted to show you because I think it's kind of fun. It's not necessarily something that you would come across a lot. I think the tools that we have are, as far as LP-Solve and LP-Solve API, are quite good. But there is a really cool package called iGraph. I use this in my academic work, and you might come across it. So I wanted to just show it to you. So you're going to want to load the library iGraph. Oops. And so we have this data frame right here. Oh, I already put it up there. I guess I'm being a little redundant today. Forgive me. So remember we talked about in class the other day, we've got an edge and we've got so here I'm basically very explicitly enumerating out the flow and the capacity on each edge. And so here I'm creating this data frame with nodes and edges. And now using iGraph, I'm going to call this graph from data. It's one of the built-in functions of iGraph. And I'm using a built-in flow called maximum, built-in program, excuse me, called maximum flow. And you can read the syntax. I just wanted to show this to you to show you how cool this product ends up being, this tool ends up being. So when I have each of these flows and edges, it's telling me how much to put through each edge. And you can backwards integrate to see what it looks like. But here's the really cool part. When you plot it, it gives you this nice visual, and you can really tweak this to your advantage, but it gives you the flow of each of these routes, and it gives you the determination on the optimal, which is really kind of cool. So that's not something I'm ever going to test or ask. I just thought you'd find it kind of cool as I did. If not, feel free to disregard that piece of random knowledge. So with that, if you have any questions, feel free to email me. All of these documents were going to be uploaded, and I look forward to seeing everybody next class. Thanks. Take care.